Okay, well now we've reviewed our Bohr notation and our standard notation, so our 282, those kinds of things, and our maximum number of electrons being 2n squared. Time to move on and add a little bit more complexity into this that will allow us to understand sort of the energy arrangements in atoms, which is really important for us to understand how they behave. One of the first things that we need to be able to do with this is to understand ionization energy. So ionization energy is defined as an element, the minimum amount of energy required to remove an electron from an atom in the gaseous state. So this is a definition that you need to know. You need to make sure that when you do define it, you include the fact that the atom must be in a gaseous state. So what this means is if all the electrons in the atom were the same energy, then it would require the same energy to remove an electron from them because they wouldn't have any difference between them, so it should all be the same. But what we see when we do this is that they are actually different. So when we measure the ionization energies, it shows us evidence for the existence of electron shells. So looking at this one here, which is actually sodium, we can see that this is the first electron as it moves, which is the lowest energy, so this would be the valence electron. Okay, remembering that sodium has 2 and then 8 and then 1, and that as we get from the nucleus out, the energy goes up in terms of how much energy they have. But this means because they have a higher energy, the further out they are, the easier they are to remove. So this first one is the valence electron, okay, which corresponds to the first ionization energy. And then what you can find is that there is a big jump between the first and the second. Okay, so this is actually indicative of us going into a different shell. The next electrons now have a different set of electron energies. So then we can take 1, 2, 3, 4, 5, 6, 7, 8. So these ones are all in the second shell. Okay, we know that they're in the same shell because they're close together. Okay, so that tells us how many are actually in the second shell, because after the 8th one there's another big jump here. So this means that we're going into a new shell. Okay, so now we have a new shell that we're going into, and this is actually our closest shell. We can see we've got 1, 2. So we can see that in this it fits that we have 2 closest to the nucleus because they require the most energy to be removed, which makes sense because they'll be most attracted to the positive nucleus, remembering electrons are negative. Then we have 8 in the middle shell, and then 1 in our outer shell, which gives us the electron configuration that we're used to for sodium, which is 2, 8, 1. So what this means is that shows clear evidence for the structure of shells, okay, that the outermost electrons are relatively easily removed. Then there is a jump in energy required to be able to remove the next set of electrons. And as we get progressively closer to the nucleus, that energy gets harder and higher and higher because the electrons are harder and harder to remove. So this successive increase in energy followed by large jumps gives us evidence for the existence of shells and the maximum number of electrons that we find in each shell. So Bohr is not where our understanding of the atom has stopped. Since Bohr proposed electron shells, we've learned a lot more about quantum mechanics and the wave nature of electrons. What this means is that our current model of the atom is more like this: a hard central nucleus, which then there is a region around the nucleus where we're 95% certain that we will find an electron. And this is because electrons, the nature of electrons being both waves and particles, they pop in and out, so they're not always in the same fixed place. They're constantly moving. Okay, so this is assuming that they behave as waves, and we know that they have characters of both waves and particles. Okay, so we take the shell idea, and now these become Distances from the nucleus, yes, but a range of possibilities within those shells where electrons can be found, and we refer to those as subshells. So if you think about these being possible shells, the subshells exist within these spaces here. Okay, so and if an electron is found in a subshell that is closer here, it will have a little bit lower energy than one that is further out. So that what we find is that there are variations within the shells themselves, and they're due to subshells. So shells are our major energy levels in which electrons are located. They relate to the relative distance from the nucleus, and they are numbered 1, 2, 3, 4, 5, 6, and 7, ranging out from the nucleus. And then subshells are found within those shells. Subshells are given special names. They have S, P, D, and F, and G. We stop at about D by just doing the first 36, okay, and they go in that order. So you need to learn this order, which you will just by practicing your electron configurations. So S is the lowest, so we go S, P, D, F, and G. And then each one of these subshells contains orbitals, and orbitals can hold only 2 electrons, okay? So we're going to and then each subshell has a different number of orbitals. So what this structure means when we step it out in terms of energy is we can relate our sort of simplified model of the atom, the Bohr model, and extrapolate it out into something a bit more complex, which is our wave mechanical model. So in shell 1, there is inside this shell, there is one subshell, which is the S subshell, and it contains 1 orbital. Then inside shell 2, there are 2 subshells, the 2s and the 2p. In shell 3, we have 3 subshells, which is the 3s, the 3p, and the 3d. And you can see here that something a little funky happens when we get up to the 3 subshells, because now as we move up, the energies get closer and closer together, and the lowest energy of the 4s subshell is actually a little bit lower than the 3d, and these are very, very close in energy. So when we actually fill in electrons, we put 2 into the 4s before we fill the 3d. And you may actually remember that when we did calcium, we said that calcium was 2, 8, whoops, can't draw an 8. The calcium was 2, 8, 8, 2, okay, and so we had this 2 out in the 4th shell, even though we said that the 3rd shell could hold 18. Okay, because remember, 3 squared is 9, and when we times that 2 because of our 2n squared rule, this would give us 18 electrons. And when we write configurations, we write them this way. For calcium, we put 2 in the 4th before we come back, and that's because of this little guy here, the 4s subshell. We put 2 into that one before we can continue to fill the 3d. Okay, so just as you had to learn the 2n squared rule, we also need to know the subshells, the number of orbitals, and therefore the maximum number of electrons, which tells us this one. So in an S subshell, there is 1 orbital, okay, which will be an S orbital, and it can hold 2 electrons. In the P subshell, there are 3 p orbitals, and they hold 6 electrons because each one holds 2. In the D subshell, there are 5 d orbitals holding 2 each, giving us a total of 10 electrons. Okay, and then in the F subshell, there are 7 holding 14. So what this means is that in the first shell, there is an s orbital that can hold 2 electrons. In the second shell, there is an s orbital that can hold 2 electrons, but there is also a p orbital which can hold 6, and in the 3 there is an s orbital that can hold 2, there is a p orbital that can hold 6. Then we hit in energy order the 4th shell and its s orbital which holds 2, and then we go back to the 3D subshell which has 5 orbitals, can hold 10. And this would be the full electron configuration up to a full 3D10. Okay, so this is actually going to go up to element number 30, and then after that we have 4p6, and that takes us to our full 36. So with our orbitals, the reason that there is only 2 is the Pauli principle, and this gives the number of electrons in any orbital, and essentially it states that atomic orbitals hold a maximum of 2. This is because electrons have a spin. They have spin down or spin up, and we can't have 2 of exactly the same thing in exactly the same spot. So they can pair up as spin up or spin down, giving us 2, but we can't have any other combinations than that. So we can have 0, 1, or 2, and that is all we can have. And this goes through our spin here. So when we think of electron spin, it's that we think of them as spinning charged particles, and therefore we can have up and down, so like poles on a magnet. So shell 1 will have 1 subshell with 1 orbital and 2 electrons. Shell 2, 2 subshells, which is our 2s and our 2p. Shell 3 can have 3 subshells, s, p, and d. So now that we've set this up, we can now start to write our electron configurations using subshell number labels and electron numbers. This is a table that outlines all of them in terms of their number of subshells and the subshells and orbitals in each. When we write electron configurations now, going forward from our Bohr electron configurations, we need to show the principal quantum number, which is the shell number, the subshell that we are talking about, and the number of electrons that can be held in that subshell, which will be 2 multiplied by the number of the orbitals, or how many it's actually got in it as we fill them. We filled them in order from lowest energy to highest energy, okay, following the same rules that we did for Bohr. So if we look at the configuration for sodium, where we said it was 2, 8, 1, now under the new rules, we would fill the 1s first, so it would be 1s2, then we follow this around and we go 2s2, because it only has 1 orbital. From there we go 2p6. This now gives me 6, 7, 8, 9, 10 electrons, getting me to 3s, and now I only have 1 electron left to put into that one. So, and now I'm full. I have done my full 2, 8, and 1 configuration. These diagrams show you how the orbitals are arranged in terms of energy and therefore the filling order. You can learn the diagram or learn the order, but you do need to fill them in this sequence and this sequence only. The analogy that is often used as this is filling electrons as though they have rungs in a ladder. So each step up is a step up in energy. So if we have a look here, we can see carbon, which has the atomic number of 12, so of 6, sorry, and mass number of 12. So we have 6 electrons. So we can go 1, 2, 3, 4, and then we leave them unpaired until we have to pair them up again, 5, 6. So moving on from carbon is nitrogen. So we pair up. So now it goes into this box here, and then we have oxygen where we've filled 1 in each box. Now we come back and put the second one in the box there, and these are referred to as Aufbau diagrams. It's another way of showing the electron configuration of an element. So essentially what you need to do is just follow the rules. Okay, going from 1 forward, S, P, D, and F, using the right number of electrons in the arrangements. And you need to be able to do this for atoms and ions up to element 36, and we will have a lot of practice on this next week. Okay, so remember, when you do this, when you work out your total number of electrons to be able to place into the orbitals, you've got to remember that if you have lost or gained electrons. Okay, it's pretty critical when we do this so that we know we have the right number, remembering that if we form cations, we've lost electrons, and we form anions, we've gained them, so they add or subtract from our total number. Just one note, and we will go through this in more detail. Copper and chromium are exceptions, which means you need to remember these two fill in a slightly different way. Okay, this is because with quantum mechanics, there's certain stabilities that we get by having half-filled orbitals rather than ones that are a little bit full or almost full. So in the case of copper, we end up with a electron configuration that is 1s2, let's do chromium first. 1s2, 2s2, 2p6. Okay, so this is my 10, then 3s2, 3p6. This 18 electrons here is represented by this condensed notation here with the square brackets with argon. This square bracket is basically saying the electron configuration is the same as argon up until this point. And we can do that with our closest noble gas, and then we add the ones on that are after there. So with chromium, we can see we've got 18, 24. So when we come to do this, after we do the 20, we would usually go here, we would go 18, then we go into 4s2 is 20, and then it would be 3d4. What we find, however, is that its configuration is actually 4s1 3d5 because it's more stable for it to have two half-filled subshells than the one full in the 4s and the partially filled in the 3d. We see this also with copper, where it would if we were writing it out in order, it would say 4s2 3d9. What we find is that one of the s2 electrons actually sits up in the 3d orbitals, giving us 4s1 and 3d10. This is simply because it is more stable that way, it has a lower energy, and things in our universe tend towards the lowest energy conformation. We will also look at excited state and ground state. So as we said before, when we do flame colors, we're exciting electrons. This means that electrons jump up into a orbital that is higher energy than normal. So if we were looking at something like sodium, where we said we had 1s2, 2s2, 2p6, 3s1, that would be its ground state. All the electrons are in its lowest possible configuration. But if we were to write one in the excited state, what we would see is that 1s2, we might see 2s1, 2p6, 3s2. So an electron has gone from a lower energy level up to a higher energy level, and we know this because one of the lower energy levels has less electrons in it than it should. So this is considered to be an excited state. So I know this has been a big video, it's a long one, there's a lot in it, but please go through and look at the questions and practice these configurations so that you can ask me plenty of questions when we get back into class. It seems very confusing when we start doing it, but it does get better, I promise. Okay, and then we will relate these to the periodic table, but I think we've done enough for now, so I will see you in class.